What about why are we talking about gold and copper? Well, gold and copper it transmits electricity. It conducts it. But what is being talked about in this article here is saying, what if it was all photons? How do you store memory in photons? How do you do compute in photons? It's actually pretty obvious for us to think about the well, so we see here that NVIDIA announced on Monday that it's investing $2 billion each into Lumentum and Coherent, which are both developing photonics technology for data centers like optical receivers or transceivers and transmission circuit switches and lasers, which are used to move data at high speed over long distances. So $2 billion each into two different companies, NVIDIA just announced. Yeah, this is a really interesting situation. And hey, let's talk physics here for a second. And I'm a physicist. This will get me going. On your iPad, on your laptop, on your phone, the connections between the chips, the memory, these are done through copper. They're laid. You have a PCB. It's fiberglass and epoxy, and then you lay down a surface of copper on it, and then you etch the copper off, and then now you have wires going everywhere that are on the surface of this board. You do this with the CPUs, with GPUs as well. Typically, it's either gold or copper that is in there transmitting the signals. What about why are we talking about gold and copper? Well, gold and copper it transmits electricity. It conducts it. So if you hook a voltage up to one side, that voltage will propagate across that wire at about 2/3 the speed of light. You'll see the voltage show up on the other side of that wire, in microseconds, milliseconds. It depends on how far away you are, et cetera. On machines, it's almost negligible. It's happening, nanoseconds, et cetera, that type of thing. Basically, a way to transmit information is, and hold on to that information is through metal on a machine, and then you put voltages on that metal, and it goes up and down. And this is how all of logic and transistors and all that stuff works today. But there is another way to think about the world. There are other things in the world other than just electricity. Optics is another way to look at this, which is, hey, instead of electrons and protons and that type of thing carrying this signal, this information signal across wires, hey, can we shine a light and use photons to do that? So we all know that if you turn a light on or turn it off, you can see the blinking, right? That blinking can also carry information, 1, 0, yes, no, et cetera, that type of thing. If you blink it in a certain pattern, then that carries information as well. Well, it's the same thing with the signals on the wires too. So electricity, they're blinking on and off, et cetera. This is digital logic is what it's called. The traditional systems now are based on copper. The way that a GPU would talk to another GPU is through copper. The way that if you set up an entire data center full of B300s, which are NVIDIA's flagship model, the Blackwell 300s, then they would typically be held together, like they would be communicating with each other across copper wires. There would be many copper wires. And a few years ago, I don't know, 3-5 years ago, something like that, NVIDIA bought a company called Mellanox, which does this. They bundled together a bunch of copper wires, and then you string them between computers, and then you can do this high-speed communication across them. Other machines talking to each other in this local network, et cetera, it's all done over copper. But what is being talked about in this article here is saying, what if it wasn't? What if it was all photons, okay? And there's an interesting thing to talk about here, which is like, how do you store, memory in photons? How do you do compute in photons? It's actually pretty obvious for us to think about the transmission of information through photons because you just do blinking lights, basically, right? But there are these other concepts like how do you do a neural network but in photons, rather than electrons, et cetera, and how do you do it efficiently and how do you make it all work really well, et cetera. That's not that second part that I was just talking about is not what this is about. You can see what they're talking about, blinking lasers, transceivers. This means transmitting and receiving, that type of thing. Switches, so like a network switch that you're communicating to, one machine is communicating to another machine over here. It would all be typically done through copper wires, et cetera. Well, what if it was done through optics? And by the way, if you're saying, wait a minute, I have fiber optic cable coming into my house. Yes, you do, okay? Many people in the world have this, but typically what is being talked about here is like, what if everything were optical? What if you didn't have to go from optical to copper, back to optical, or copper to another copper, et cetera, that type of thing? Can we put it all into just like one fiber optic line, or not have to do these jumps? And the jumps from optical to electrical. And the jumps from optical to electrical cost energy. They cost time in order to do them. And then you have to do error correction on it and that type of thing. And so anyway, like what they're betting on is just a physical principle here, NVIDIA, and they're saying, man, copper is really reaching the end of its limits here. You can keep bundling together more copper wires, but you actually can't get more out of a copper wire anymore. So like they have strung the copper wires from machine to machine, but when you start to saturate the communication there, you say, well, just add another copper wire. Well, okay, we'll add another one, add another one, add another one. Now you have huge bundles of copper wires trying to transmit this information, and it literally, like machine to machine, there wouldn't be enough copper wires coming out of it in order to do the transmission. You have to think, okay, how can I possibly change this? Well, optics is a way to do that, to say, well, optical information can actually hold more, and you can do it. You can have different colors of blinking lights, et cetera. Like there's a whole world here, which is silicon photonics, just optics, fiber optics in general, that have only really been used right now for long range, high throughput, but high latency type applications. And now they're trying to take that idea, and they have been for years, by the way, for the last like 2 decades, people have been talking about this. Physicists know that this is a fundamental limit, and optics are better than copper if you can do it, but if you can do it is the hard part, okay? And this is why it takes $2 billion. You give it to the companies, and then you say, hey, you've done great work over the last 2 decades, let's pump it up, because the data centers need this now. And so this is what it feels like with NVIDIA right here. So there's a question here. Does this $4 billion bet reveal that the interconnect, not the chip density, is now the real infrastructure constraint? I'll say yes and no on this. So if you're talking about scaling up in data centers, having multiple machines talking to each other, then yeah, this interconnect is probably the limiting factor now, or one of the big limiting factors. Another is, how do you get the energy in, and how do you get it out, the heat, okay? But the interconnect is becoming a really serious problem in that. But I'll also say, no, not really, in another way, because memory bandwidth is the more visceral thing that these models are running up against. So the models are getting really large, and the compute is getting really fast, and the compute keeps scaling, and you can sort of scale horizontally and through SIMD, single instruction, multiple data. This is what NVIDIA does with their parallel processing. But through those techniques, they can just keep scaling horizontally, making the chips bigger, et cetera. And that's working really well. They keep hitting their trajectory that they wanted to hit over the last decade. But the thing that hasn't been keeping up to that scale is memory bandwidth. So memory keeps getting larger, but the communication of the information off that memory into the chip is becoming the bottleneck. So if you're wondering why a large model, it's like 1 trillion parameters, or 600 billion parameters, or 400 billion parameters, if you have to take that 400 billion parameters, so think a terabyte of information, and then send it to the chip, do a computation, and then destroy it all, and then send it again, and do et cetera. This is a very wasteful process. It takes a long time, et cetera. So anyway, the chip, the actual computation of LLMs, agentic flows, et cetera, they're more limited by the memory bandwidth right now. But NVIDIA isn't looking at the problem of literally today, because that's a problem of today. But they'll fix that with more memory, a wider memory bus. They have ways to address this. But hey, can you make the communication of the memory to the GPU faster through silicon photonics? Maybe, right? Can you make the machines communicate with each other even better, and then you scale horizontally that way, and then now you can add up the memory bandwidth of each of the machines linearly. So let's say you have 100 machines, now you want 200 machines, well, you just double your memory bandwidth, right? As long as you can communicate between them very quickly, right? And that's where the interconnect comes in. So they're hedging their bets on multiple frontiers. Hey, let's improve memory bandwidth on device, sure, but then if that doesn't work, let's do it through interconnect, et cetera. So it's a few things at once, but the interconnect is a big one. If you want to learn more and keep up to date with this quickly advancing world of AI, go ahead and comment, and subscribe. There's new episodes every week.